Finally, we come to the climax of a first semester calculus course. This is the point where we finally make explicit the connection between derivatives and integrals. From a casual glance, if one naively views both concepts graphically, then it's like asking for a connection between slopes of tangent lines and areas under curves. What's the connection? Stated that way, it's not so obvious, but after our discussion here of the fundamental theorem of calculus, you should come to view differentiation and integration as flip sides of the same coin. So this theorem has two parts. First, we talk about part one because it's the more logical and natural place to begin. But it's actually part two that you'll probably find more useful. So here we start with a function f, little f. This part of the theorem says, roughly, that if you integrate little f and then differentiate it, you get back the original function, f. Part 2 says the reverse, starting with a function, if you first differentiate it and then integrate it, you get back the original function. So it takes just a little bit more care to state it properly, but the way I've paraphrased it should help you to remember the general plan. Now, we started with little f, and I'm going to denote by capital F of x this integral from a to x of f of t dt. Now, usually when we integrate, we've been talking about integral from a to b, and then we just get a number. Now, here comes some of the fine print. Instead, we're going to integrate from a to x. So you get a number, but it depends on x. So I'm calling that capital F of x, and it depends on little x, so it's some kind of function of x. I'm assuming, of course, that a is constant. Now I want to reserve the letter x for the right endpoint of the interval, so I need a different name for the horizontal axis, and I'm going to call that t. So that's my independent variable. I'm going to say that my graph is y equals f of t. It doesn't really matter how I label the axes. It's just the shape of the graph that's important after all. So if I integrate the function f from a to x, I get an answer that depends on x. I'm calling it capital F of x. You can actually just pretend that this is a positive function so that capital F is just the area that I've shaded here in blue. And then what the theorem is telling us is we need to take the derivative of this function, capital F. And I want to show that that derivative is little f. So I go ahead and do that. I write down the derivative of capital F. Now let's see what this says. The first thing is capital F of x plus h. Well, that's the area from a to x plus h. Whereas capital F of x is just the area from a to x. So I have two different areas, and I'm subtracting. And so when I subtract off and divide by h and take the limit, that's what I'm looking for. But of course, if I subtract those two areas, then all that's left is this vertical strip that's now shaded in brown, the strip between x and x plus h. So what's the area of this strip? That's the question. Well, of course, the width of the strip is h. But what's the height? Well, you could use the height on the left or the height on the right, f of x or f of x plus h, or to use something in between. Now, this is a lot like taking Riemann sums, where you ask, do you take a left Riemann sum, a right Riemann sum, a midpoint Riemann sum? And from that discussion, what we learned is it doesn't matter which one we use in the limit. And something like that is true here as well, that you can just approximate this strip as a rectangle, and in the limit, you're going to get the right answer. That's the intuition, and there's some details that I'm fudging a little bit. So I replace the vertical strip by this rectangle of width h and height f of x. That's not exactly right, but just like in Riemann sums, it'll give you the right answer in the limit. So I'm leaving out the minor details about why this approximation works, but at this level of a calculus course, I'm not committed to giving an actual proof, just the ideas are okay. So I think this explanation is good enough for us. Now, after making this approximation, the area, which is the numerator here, becomes rectangular area base times height, and f of x times h. I have an h in the denominator. They cancel, and obviously the limit is just little f of x. This is the answer that the theorem says we should get. So I have explained, almost proved, but glossing over some details. So let's just say I've explained how the theorem works, why it works. And now, let's paraphrase. Starting with little f, the derivative of the integral of that function is the function we started with. So glossing over the fine print, this is a way to paraphrase the theorem. Let me say a little bit more about what our theorem is about. And once again, I'm going to use capital F for this integral inside the theorem. So it's the integral from a to x. Now the theorem says that the derivative of capital F is little f. In other words, capital F is an antiderivative of little f. And we learned to write that this way. Antiderivative of little f is capital F plus a constant c. You don't know which constant, there's some constant. Actually, our function capital F, when we wrote it down, it depended to some extent on which starting point we chose for the integration. And I wrote down A. What point A do you use? Well, if you use a different point for the left endpoint of your intervals, and it's a constant, but which constant you use will have some bearing on the capital F, the antiderivative you get. But different choices of the left endpoint for little a just give you different antiderivatives that vary by some constant. So it's just the constant c that changes. The constant c we call the constant of integration. So it's the constant of integration that is different depending on what starting point you choose for your integration. Now we're ready to look at the second part of the fundamental theorem, and it's kind of the reverse of the first one. So I'm going to start with, again, a capital F and a little f. Capital F derivative, capital F prime is little f. So capital F is the antiderivative of little f. That's the context. Same context as before. And now what it says is you have a way to actually compute integrals of little f on an interval, let's say from a to b, if you know an antiderivative, capital F. Namely, you take your antiderivative, you evaluate it at the two endpoints, and then you subtract f of b minus f of a. Now from what I'm saying here, there are actually more than one antiderivative, but it doesn't really matter which one you take, because if you take a different antiderivative for my capital F, it's going to be the same thing up to a constant. And if you make a constant added to capital F, then by the time you compute the right-hand side here, you're subtracting and the constant goes away. It just cancels. So ultimately, it doesn't matter which antiderivative you choose. Now in part one of the theorem, I was a little bit more specific about my choice of antiderivative. And here, I don't really care, because as I've said, different choice of antiderivative will give you the same answer anyway. So capital F is just any antiderivative for little f. Now, from part one of the theorem, I know that this integral from a to x of little f, that's an antiderivative. But now I have some other, possibly different antiderivative, capital F. So Well, they have to be the same thing up to a constant. So I'm going to write that down by saying the integral from a to x, f of t dt, must be equal to capital F plus a constant capital C. But now I have enough information to determine what that constant capital C is. Well, how do I do that? Look at what happens when x equals a. Because now you have the integral from a to a, which equals 0. On the left-hand side, you have 0. On the right-hand side, what do you have? You have f of a plus c. So that has to equal 0. And use that to solve for the constant c. c equals minus capital F of a. And you can plug that into your formula above. Now it's time to also evaluate at x equal b. When you do that, you get the integral that we're looking for in the theorem. The integral from a to b, f of t dt. And that equals f of b, capital F of b, plus c. And you know what c is, so you substitute that in. You get f of b minus f of a. That is what we were looking for. So, as I said, this theorem is very useful for integrating functions if you happen to know an antiderivative. In our next video, we'll put the theorem to work. We'll compute some areas of regions that you were never able to calculate before. So just to recap, our theorem says if little f is the derivative of capital F, I take note of that in my formula. I replace little f by capital F prime. Now I'm going to make one other change. I'm going to replace the b by an x. And that's just so I can say that if I take the integral of the derivative of capital F, then I get capital F back, plus a constant. Okay, so to emphasize this paraphrase of the theorem, it says the integral of the derivative of a function is the function that you started out with. Okay, that's how I paraphrased, well, up to a constant, plus a constant. So this is the nutshell version of the theorem that I paraphrased for mass consumption earlier. So congratulate yourself. You have reached the climax of a first semester calculus course. Go and celebrate a little, have a drink or an ice cream sundae or something. And then in our next video, we'll work through some examples using the fundamental theorem.